Eugene to tell us about smooth correspondence between quiver and varieties.
All right. Thanks again for inviting me. It's always great to be here. For a change, I decided not to talk about non-homology and talk about something else. So this is a joint work with Jose Simental, who is in Mexico, and Nicolle Gonzalez, who is now in UBC. And there are two papers. So one from this year, where all the geometry it is, and that's kind of the main bulk of the talk, where I'll talk about actual geometry. There is algebraic thing, which is partially written in that paper, like for the Hilbert scheme case, and I'll explain what's actually in this paper. And then there is forthcoming paper when we're writing this for general quiver as well. Okay, so what is the setup for geometry? So first of all, I want to remind you of some basic facts and definitions about quiver varieties. So Q is an arbitrary quiver. So loops are okay. Multiple edges are okay. Everything's okay, whatever. Like really any quiver we want. So then I want to define Nakajima quiver variety. So it will depend on two vectors, which I'll denote D and F for some stupid reasons. So this is Nakajima quiver variety. And it parameterizes the following data. So first of all, for each vertex, E in the quiver, we get a vector space, which I will denote by dV, and a vector space, which I'll denote by FV. So this is the framing. And I want the dimension of dV to be little dv, the dimension of FV to be FV. Right? So for each edge, E from V to W, we have a pair of maps, which I would call AE. It would go from dV to dW, and BE should go from dW to dV. And then for each vertex, we have a separate pair of maps, which go, so I have IV would go from framing to dV, JV would go from dV to the framing. And I think that's all what we have. And now we have some constraints. So the constraints come from the moment map equation. Which is the sum negative. So if I have the sum of all edges from V to W, and I get BEAE plus the sum of AEBE, where I have all edges from W to V, and then maybe plus IV and JV is equal to 0. Okay, so this is a moment map equation for the group actions. We have group, which is the product of GLDV. And this is the moment map for this action, and I want to set it to 0. And then finally, I have stability condition. Which maybe I won't write explicitly. I mean, people have seen this before in many settings. So basically, my stability condition always, I start from the framing, then I apply this map IV, and then I apply A's and B's in different combinations, and this thing should span my spaces. So this is the usual one, but sometimes, especially in old papers, Nakajima used different stability conditions. Whatever, we use just one, and let's not focus on that. And then, of course, my space is just, so this MQ of TF. So this is mu inverse of 0. So this is this condition. Then I put stability condition and of course my Yes, exactly. So that's kind of the big result of Nakajima. That the space is smooth whenever it is non-empty. And there are some formulas for dimension. And the tangent space. And all that. But kind of the key thing, and especially the key thing for me today, is that this is always smooth. It could be empty. There are some criteria, like due to the work of Nakajima and Crowley-Boley and other people, will say when it's empty, when it's non-empty. But in this generality, you can classify when it's empty, when it's non-empty. Whenever it's non-empty, it's automatically smooth. And so this is kind of big breakthrough result from, I don't know, 97, 98, some around that time. So that's cool. So we have a lot of interest in smooth spaces where we can study geometry. And we'll have two running examples, which are too easy, but I don't know, but hard examples. So one easy example is when I have just this. So I have the framing N, and then my vertex, let's call this D. So I have no, so my quiver is just 1 point, all right? So for this point, I have my dimension vector D, I have my framing vector N, and I have two maps I and J. Then my stability condition says that I is surjective. And my moment map equation says that Ij is equal to 0 because there is no A and B, there are no loops, and no map, no arrows. And so then I can say, well, so how do I encode this? Maybe it's worth spelling this out. So I have the vector space, let's call this V. So this will be the kernel of I. Dimension of V is N minus D. And then on this space, I have an operator alpha, which goes from Cn to Cn. And alpha is just Ji. And then the point is that, so I have Cn, inside I have V, inside I have 0, and my alpha acts like this. So alpha of Cn is contained in V, and alpha of V is equal to 0. And of course, we get just T star of the Grassmannian, so my moment, my MQ, in this case, is just cotangent bundle to the Grassmannian. Okay, so that's my normalization. Again, sometimes people use slightly different stability conditions and slightly different things, but here I'm saying, okay, so I is surjective, the kernel is N minus D dimensional, and then I have an extra operator which does this, all right? And then another running example will be the Hilbert scheme, of course. So I have just 1, and then here I would have N, I have I, J, and then I have whatever, A and B. And my moment map equation will be the commutator of A and B plus Ij is equal to 0. And my, maybe I don't want to explain details, but everyone knows this. So this is the Hilbert scheme of n points on C2. And this is, of course, smooth. And kind of one fancy way to prove that it's smooth is actually to realize this as quiver variety. And then basically check. So I mean, the whole proof of smoothness, so going back to your equation, just like you compute the differential of the moment map and check it's surjective under stability conditions. So it's linear algebra, but it's not super complicated. All right, so now I want slightly more complicated. Any questions at this point? Everyone's have seen this, I think, in this room. Good. So now I want to move to something more interesting. So in more interesting things in Nakajima correspondences, which also define by Nakajima in the same papers. So let me phrase it this way. So now we have a pair of, of these things. Let's call this of representations, but I'm not saying representations of what? D0, D1. So and the framing is the same. So first of all, yes, so dimensions something like D0, V, and D1, V, and the same framing, V. And then there will be some constraints on this, but I'll say it in the end, maybe. Then what I want to say is, so you have surjective map. Let's call this pi v, which goes from D0 to D1. For each v. Then we have a condition that, of course, this surjective maps, maybe I'll write it for this. So this commutes with all this data like I, J, A, E, B, E in appropriate sense. Right, so you just have a morphism of all this data. So I'm saying, so this, in particular, this has maps A's and B's and I's and J's. This has map A's and B's and I's and J's. And the map pi intertwines them in appropriate sense. Then kind of D0V and D1V satisfy, or just D0 and D1 really satisfy moment map equation. And stability condition separately. So you can save a little bit, like the existence of this map already guarantees that like if one is stable and the other is stable, so but let's put both of them, it doesn't matter. And then kind of the most restrictive condition, which I was hiding until the end, is that dimension, so this, let's write it this way, so dimension of D0V minus dimension of D1V is equal to delta VW for some fixed vertex W. So this means, in particular, that my dV0 is actually equal to D1 V if V is not equal to W. So outside of my one fixed vertex W, I don't change anything at all. And then at this vertex, I'm allowed to change it, but I'm allowed to change it exactly by one-dimensional subspace. So this is extremely restrictive, of course, but that's okay. And so in this setting, what Nakajima proved, let's give it a name actually. So let's give this M to Nakajima. Oh, I don't know, D0, D1, F. Nakajima is that MQ is smooth, okay, if non-empty. And then he did a lot of other computations. He computed dimensions of this thing, various tangent spaces, various interesting operators. We'll talk about this a bit later. But again, you have a nice smooth space. And of course, you have a nice projection from this space to Q of D0. Let's put D1 here. Okay, so I can forget one of them, and then it still satisfies moment map equation, satisfies stability condition, so it still gives you something nice, and of course it is smooth. And so the point is that, so this space is smooth, this is smooth, this is smooth, and we know pretty well this whole diagram, what the maps do. in every single situation. All right, so that is the thing that we want to generalize. And maybe one example, which some people might have seen. Is for the Hilbert scheme. So you got Hilbert scheme of n and n plus 1 points, which is really just pair of ideals in C of xy, and dimension of C of xy mod I is n, and dimension of C of xy mod j is n plus 1. And so this surjective map, in this case, it will be something like C of xy mod j surjects onto C of xy mod I. So, because like in quiverized, you really work with the quotients, and so if I have this inclusion, it corresponds to surjective map from here to here. And the kernel would be like I mod j one dimension, okay? And then this space is smooth, and again, like lots of people here, like this a lot, so this is nice and smooth. And so kind of the obvious warning here is that the Hilbert scheme of n and n plus k, if I do the same thing, but now codimension is equal to k, this is very similar. And I mean, it is singular for k greater than or equal to 2 if like it's 2 or 3 people have some methods to control singularities. If k is large, nobody knows anything about singularities.
For these kind of things, cotangent from the corresponding C-star action, which scales the symplectic form.
Yeah.
Is it true for all of them?
Yeah, you have an interesting sister action. Maybe I'll say this. So you have a lot of interesting sister action. So, okay, so you have, first of all, for each framing vertex, we have kind of, I mean, we have GL of F, but we have maximal torus there, so you have kind of C star FV. But that's maybe not super interesting. You also have some equivariant parameters. Let's put a TE for each edge of my quiver, of the original quiver. And so in particular, the AE has weight let's say TE. BE has weight QTE inverse. So you have additional parameter Q, which is related to the weight of the form that you were asking. And then also I has weight 1, I think. That's the usual convention. And then J has weight Q. And so with these conventions, my moment map should be homogeneous because A and B multiplied with the weight Q, B and A multiplied with the weight Q, and this multiplied with the weight Q. So you have a lot of different C stars from the edges, and then from the framing, you have a separate wealth of C star actions which are there. And in particular, you can study, so the fixed points are usually non-isolated, but you can still study equivariant cohomology, equivariant K-theory, whatever, and we'll talk about this.
Which of these preserve this correspondence?
All of them. So this is everything you can make equivariant. So there is an action on correspondence. So everything is equivariant with respect to this thing, and so you have this wealth of parameter. Like you can, like, if you're, for example, if your quiver is a tree, you can scale away these things by some gauge transformations. So maybe you don't want all of them, but like a priori you have all of them. And then if you have a lot of interesting cycles in your graph, then you have lots of interesting things that you cannot kill by gauge transformations. But like kind of the minimal thing is this. So in particular in this setting for the Hilbert scheme, of course you have just two parameters q and t, and one corresponds to kind of the q for this I and j thing, and then t is in this case the weight of the loop. It's like slightly rescaled, but like basically weight of x and weight of y. And then this correspondence is still equivariant with respect to both of them, right? It's still, you can rescale x and y, and that's fine. And yeah, so everything will be equivariant with respect to this big torus, and that's fine. Good question. I mean, if you have like more things in here, there are even more singular usually. That's bad. Yeah. You can have like n plus 1 and plus 2. That's singular, but like people study these singularities and like think it's complete intersection or something, but it's just messy. And then again, if k is general, you don't know. Okay, so here's a new construction. I mean, again, like if k is small, it's kind of, people worked on this. But if k is arbitrary, like I don't know any. So yeah, that's singular. That is singular. I think like what Vivek was saying is that it's not really badly singular, which is probably true. We'll come to that, but yeah. Maybe I'll put it here as well. I think the answer is like if k is very large, then probably yeah. I don't know if anyone knows anything. No, I think for this nested ones, my bet would be yes, actually. Yeah. For n and plus k, maybe you have some chance. Yeah, I don't know, but like I don't know. I mean, again, it's a question like I mean, how bad is bad? But it's like people study this kind of thing, I know, and like people actually use this for some computations with this correspondence because. I mean, we'll talk about this, but like once, so these are correspondences that define for you some operators between Hilbert scheme and the next Hilbert scheme. If you want to study relations, you need this kind of things, but these are just hard. And so that's where the meat is. And so Yuzhao in particular, so he's former student of Nicolle, he did a lot of work on this, and Nicolle himself did a lot of work on this, but it's hard. Yes? So you have C star action, like, so you have C star to the number of edges plus 1 plus, so this, you have an action of a big, very big torus. Yeah, so the torus action, so when I'm saying that AE has the weight TE, then you're saying like, okay, you just have an action of like separate C star, which scales that particular AE by TE, and that particular BE by T inverse, right? And times Q, whatever. But Q is a separate torus, yes. Okay, so you have lots of these things. All right, and again, like it's really, I mean, it will be important for us later when we get to that, but somehow we want all these ways to be generic, so we really want kind of maximal torus action. We don't want to specialize these T's to anything because otherwise you get some problems.
So what kind of space is this that's correspondence space that Nakajima defined? Like, I mean, the Nakajima quiver varieties are scalar.
These are Lagrangian correspondences between them. Between two hypercarrier things, yes. So these are like holomorphic sublectic, you can say, and these are Lagrangian correspondences between them. I think that's true. Yeah. Yeah. Okay, so now new construction. So again, I have a pair of correspondences, pair of representation. So D0 and D1. And it still satisfies all these things. So you have dimensions are given by something, you have surjective map, and then you have moment map, stability condition, whatever. And now the new thing is that your AE, BE, and JV vanish on the kernel of the projection map. And but kind of this is bad news because we want some restrictions, but good news is that the dimension, the relative dimension between D0 and D1 could be arbitrarily large. And so there, the relative dimension was like 0 or 1, and 1 exactly in one place. And here I'm saying, no, I actually can do any relative dimension, any vertex, and like no constraints on this whatsoever. The main constraint is on the maps, and that the maps should actually vanish on the kernel of this projection map. So what does this mean? So let's unpack. So this means that my maps AE, BE, and JV, they actually factor through this D0 mod the kernel, which is just D1. And so we get the following pictures. So for the framing maps, I have this D0 V, and this surjective map to D1 V, and I have the framing map somewhere here. So I have a diagram like this. So I can say if I want to compute my I map, I just go to here. This is I map for D0. I map for D1 will be actually the composition of this map and this map. So that's fine. Maybe I don't want to even draw this separately. Now what is the J map? J map for D1 is this, but J map for D0 is just composition of projection and the J map. And the same things for A's and B's. So if I have an edge between V and W, then my A now goes kind of from here to here. My B goes from here to here. So I project down. So if I want to define my A from here to here, I'm saying I go down, and then I go by this map AE. And here I go, if I want to map from here to here, instead I want to go like this and then project down. And then the same thing in the opposite direction. So my A's and B's are now effectively given by some rectangular matrices of size this by this. Okay, and then, but they still satisfy my moment map equations, they still satisfy stability conditions, and then they satisfy everything else. It's just like we have this restrictive condition that they factor through the quotient base. And so that's what it is. Okay? All right, so this is the construction. So that's what we kind of want. And then the theorem is that this actually works. Where was the theorem? Yes. So this is smooth. And again, I want to emphasize, so kind of the big plus for us is that this is smooth, and you can have arbitrary closed relative dimension between D0 and D1, and they're still fine. And kind of the downside is that, okay, you have some restrictions here and here, and I'll talk about restrictions and examples in a sec. But I think...
Are you also varying pi or pi? Is projection map or...
Projection map is part of the data. Yeah, but like, I mean, secretly you also have like gauge group here and here, so like up to gauge group, we're allowed to vary pi, yes.
Can you remind what is the algebra?
Oh, we'll get there. This is all geometry. Yeah, we'll get to the algebra, yes. Okay, all right, so that's the definition, and that's the statement that we'll always get something smooth. And then, yeah, of course, we can compute dimension. We can compute tangent space. I don't want to write formulas, but they're in the paper. So let's do examples.
And probably composite.
Huh?
They probably nicely composed automatically.
Kind of. I mean, we know how they compose, and they don't exactly compose to Okay, so there is some variation. I'll talk about this, but yeah, we kind of understand how they compose, but there is some extra like excess intersection. So like, but you can control this somehow. They're composed not exactly to the same things, but they compose controllably, and I'll talk about this in a second. Yes. Okay, so I'm actually erasing this example. I need it right now, so stop erasing this. For example, if I have a picture here, so I have, okay, so I have the actual vertex D, let's say D prime. So I have my framing and my I here, my pi here, surjective, and then I have my J backwards. And so in style of what I just wrote, maybe I'll repeat the necessary things. So V is the kernel of I, and this has dimension n minus D. So I is still surjective, so my Q is still 1 point. And then I have V prime, which is the kernel of I, pi I, and dimension of V prime is n minus D prime, and then this is surjective map, so D is at least D prime. And so now the picture is that we have my n-dimensional space. Inside I have V prime. So this is bigger than this, and this contains V, and this contains 0. And now my alpha wants to go like this. So it goes from Cn to V, but it goes from V prime to 0. So you can unpack those definitions with arrows and say that we want something like partial flag with 2 steps, and these are dimensions that are there. And then alpha wants to go from this to that, and then from this to this. Okay? And again, alpha is like whatever, composition of I and J. So this is a really easy exercise. In particular, in this case, it's kind of obvious that it's smooth because whatever the dimensions are, like if I fix the flag, it's just a vector bundle over partial flag varieties. So this is obviously smooth.
In this case, anything you could agree.
That's also true. That's also true. Yeah, yeah.
What is alpha?
Alpha is this composition kind of all the way here. So alpha would be like J pi I. Okay? Yeah. All right, and so for the Hilbert scheme, maybe I don't erase this, but I'm saying that, okay, so now I have my 1, I have my, maybe I don't want to write this, but I'm just saying this. So this main space will be the following thing. So this is the set of ideals inside J. So such that, okay, I and J are ideals. Dimension of C of X, Y, what I is something, whatever. Maybe I don't want to care about the dimensions. I just want to say that Xi is inside J and Yi is inside J. Okay, so this is the condition. So kind of this A and B are multiplication operators by X and Y. And if you unpack the definitions, you're saying you have a pair of ideals, you fix the dimensions, which are given by dimension vectors. And then this is non-trivial condition that X and Y kind of kill the quotient of I mod J. And that's what this is saying. Maybe equivalently, you can say that X and Y annihilate I mod J. And then again, this is less obvious that this thing is smooth. Like, we actually didn't expect this, but this space also considered in this case so this is very, I mean, essentially it's the same space as considered by other people, no, Nakajima, Yoshioka. So there was kind of intermediate space for sample crossing things, which was kind of not obvious that it's related to this. And also a more recent paper of Bayer, Chen, and Jiang. And they studied resolution of singularities for some Bernoulli loci, which I don't want to define because we don't need this. But there was some like pure algebraic geometry equation related to the spaces. And again, this space is smooth. And if you ever want to think about fixed points, as I do, you can say, what are the fixed points here? Well, I have ideal. This corresponds to a diagram. Now, what does it mean that I have a pair of ideals? I have like ideal in another. But then this condition means that all the boxes in the quotient, they're separate from each other. So I can have a box here, maybe a box here and box here, but kind of no two, and they're marked, let's say. So no two marked boxes next to each other. Okay, that's pretty cool. I mean, is it cool or is it not cool? But like this is the condition that I have like a diagram plus a bunch of edible boxes for this diagram, but these boxes are not allowed to be next to each other, otherwise you violate this condition. And it is kind of restrictive, but at the same time, it's nice. And if we have just one box, this means that like it's not restrictive at all. One box could be anywhere. And so we do recover Nakajima correspondence, of course, this way. And so this is the statement. This is nice observation. So if we essentially recover Nakajima correspondence, a special case. And the point is that, so if I know that D0 mod D1 is one-dimensional space at vertex W, let's say, right? So that was Nakajima's condition, that like we don't impose that conditions on the kernel, but instead we're just saying that the quotient is one-dimensional exactly in one vertex. But then, okay, so if I have any arrow from this vertex to another vertex, that's 0. So there's nothing to check. If I have a loop here, we need to be careful. But basically, so each loop at the vertex W is a scalar. So this is kind of 1 by 1 scalar matrix. And this matrices could be anything because my moment map equation, like the scalar matrices automatically compute. And so they don't affect the moment map equation, they don't affect anything. So up to the choice of the scalars, Nakajima's condition is exactly what we want. So we want all the scalars to be 0. They want to be anything, but of course we can just shift the matrix by the scalar and it doesn't affect anything. And it doesn't affect moment map equation. So Nakajima correspondence is slightly thicker than our because you can choose this thing. And again, if you think about Hilbert schemes, this is the difference is that there we don't require that this quotient of J mod I is at 0, and here we do require, but we can shift the quotient point to 0, and this is free. This is like this. If you have just one point in the quotient, we can always shift this. So maybe I'll just write this. So this Hilb n plus 1, this is C2 cross Hilb n plus 1, 0. Where this is where we require that J mod I is supported. Just shift it like parallel translate. And then the same argument works in general, and that's kind of what happens here with the loops.
Well, I understand this kind of correspondence as
we can. Yes. That's a good point. Yes. So let's actually write this down because that's a very good point. So another node. Yes. So we can say so we have sequence of representations. So this is the kernel. So you have D0 and then you have D1. And this is a trivial representation. So this is surjective. This is basically the pi thing. And then the kernel is a trivial. It's really trivial representation of, I mean, basically of double quiver if you want to be precise, because like you have all these arrows, A's and B's, but basically, yes, so it's of A's, B's, and so on. They all act by 0 in the kernel by design. And so this means that, yeah, we just have two things, but in some sense, this is an extension between trivial representation and some other representation. But yeah, you need to be a bit careful about stability condition, but this is really equivalent. And this is like important consequence that the kernel is really trivial. Okay? Good. Great question. More questions about this?
You don't want to mess around with the difference and all the heaps and
You can.
that.
Yeah. Yeah, that's right. Yeah. Yeah. All right, and then kind of one last thing I want to say about geometry. What I say? Doing on time actually. Good. So one last thing I want to say about geometry is the full invariant. Which I think what Mina was asking at some point about compositions. So I can now, what if I have a sequence of things? So all of these are surjective. And then I can say maybe the whole composition. So this would, I don't know, be 0, 1, and then my P is the composition. And then I'm saying that, so we fix these dimension vectors. For each of them, we can put A's and B's and I's and J's, and everything is nice and commutative, as in that diagram. And now the key condition would be that A, E, B, E, and J, V vanish on the kernel of P, of the big map, all right? And this is also useful if you want to consider different flags and nested things, but it's kind of, it's not that bad actually, because it's really conditioned about the first and the last. So basically we're saying that you have this space, we can just forget, and we get just D0 and D last. And they really live in the space that I was just defining. And then all these middle guys, we can choose absolutely arbitrarily. And that comes from this condition, what Peng was saying, that like the kernel was trivial. So we just have like arbitrary partial flag or full flag, whatever we want to do in between. But because in between like everything is trivial, we can choose the flag arbitrarily. And so the fiber, just the product of partial flag varieties. Okay, so if I know the first, if I know the last, I can choose all the stuff in between completely arbitrarily, because any submodule of any subrepresentation of trivial representation is trivial, and I have no, and it's automatically invariant under A's and B's and everything, so there is no extra condition. You can check that kind of stability is only controlled by these two guys, monotone map equation controlled by these two guys, so there is nothing new happening here. And so in particular, this space is also smooth. And this is kind of more complicated nested correspondence that we want to study. But it's not like, from this geometric viewpoint, it's not that different from just this thing. Okay, all right. Any questions?
If you do the other way, like just require each individual step to satisfy that condition.
Oh, that's more complicated, yes.
Is that too smooth?
No, I don't think so. No. I mean, that would be precisely this kind of n plus 1 and plus 2 thing, right? You have the Hilbert scheme and you're saying, okay, so each individual is stable and then the quotients are nice, but like, that's bad, yeah. I mean, you can ask how it's like defined inside this thing, but yeah, it is subtle. All right, okay, so I think that's all what I want to say about geometry. There's a lot more nice formulas in the paper, how to actually compute the tangent spaces and everything. But again, like the proof of smoothness is not that different from Nakajima's. You have to kind of chase through all these arrows, and then you have to compute differential of the moment map eventually and check that this is surjective, assuming stability, and then it all just works fine. But yeah, tells you some other things which maybe I don't want to explain. Okay, so part 2 is algebra. And so we want to define some interesting algebra acting. So now let me write the sentence and then explain. So Nakajima correspondences and line bundles on them can be used to define the action of K-theoretic Hall algebra on the direct sums of equivariant K-series of this space Q. Take direct sum over G. Okay, so you fix your framing vector, you sum over all dimension vectors, and then you get a lot of spaces. As we discussed somewhere, there is a big torus section. We take the huge torus section, whatever is available, take direct sum of all these things, and find out what is the algebra X in there. And so concretely, we can say, well, so we have this MQ Nakajima of G, let's say G minus delta W F. I have two projections. So just quiver varieties for G minus delta W and F. Let's call them P plus and P minus for some reason. And then one here, we haven't talked about this, but we have a line bundle given by the quotient, which is this D0W mod D1W, right? So if so we talked about this, that by definition of Nakajima quiver varieties, the quotient is one-dimensional. It's supported in one vertex W. It defines, so this one-dimensional space defines a line bundle on the whole moduli space. And we can use this line bundle in two projections to define interesting operators. So I can define EM comma W to be, what is this? P minus push forward of line bundle to the power M. Let's call this LW also. Tensor P plus pullback. Blah. And this would go from K theory of MQ G minus delta WF K theory of Q GF. So this would in particular increase the dimension vector by 1 at this point. And we can have a generating, so these are generators of KH in this representation. And then relations are kind of tricky.
What this looks like. So should I think of it as somehow D1 sitting inside D0, and then everything else is just like a trivial representation of the quiver? Is that what's going on?
I mean, the quotient, yeah, everything is trivial. I think about this is that, yeah, so you extend the basis of D1 to basis of D0 if you want.
Yes.
But then your matrices for arrows, they are rectangular because they start from the small space and they end up with the bigger space.
But
and so that's all. So you're saying
rectangular, but wherever they're not square, they're 0.
yes. No. They're not. They're actually rectangular. I mean, they're like. So I'm not sure I understand.
So in the part of the arrows, they go from D1 like
Yeah, so there was this picture where you have like D1. Yeah, so I mean, you had this map, right? But like this has different dimension from this one. And so I'm saying, yeah, so if I want to go kind of from here to here, like, I mean, maybe V. So there will be a matrix, but there will be a bunch of zeros in this matrix because some stuff will be in the kernel and it will just die. So there will be some zero columns for this thing. And then for this thing, there will be some zero rows. But then essentially, like, you have just some rectangular matrix, and then for the, if you go to here, from here to here, you append some zero rows, I think, and for the other one, you append some zero columns. Okay. But this is still not a square, like, unless they're the same. But like, even if it's a loop, it's a rectangular thing, because like, it really goes from different things. Yeah. Yeah.
What happens is one point between another point, and the condition that the quotient of the ideals of these points has no algebraic structure. It's just x and y both.
Yeah.
In general, because it has some module for x and y and 2x, y, and that. So this must have some direct meaning.
Absolutely. I mean, that's a good question for you all. That like, I mean, what is the physical meaning for this? Like, it's not. I mean, I was very surprised when we actually figured out that it's smooth. Like, I was sure that it's not smooth. I don't know. In general, I'm a very skeptical person, I think. But it's like, it's not every day you see a nice smooth correspondence between varieties and their generality. So like, there must be something kind of. Yeah. And yeah, so I mean, this is an example. I don't know if it's worth saying this, but yeah, so you have some bases. So I don't know, we can label them things, right? 1, 2, 3. And so then if I want to multiply it by x, what happens? So 1 goes to 2. I'm saying that, so the big thing is, so I have ideal inside ideal, right? So this is Yann diagram inside another Yann diagram. Okay, so I is this ideal corresponding to this Yann diagram, all right? J is the ideal corresponding to this Yann diagram.
Just to remind people, the people here is encourage you to
all right. Okay. Maybe you should have said this half an hour ago. Okay, all right, let's talk about ideal. Okay, so you have C of xy, right? So what is an ideal? Ideal is subset I, so that x sub I is inside I, and y times I is inside I. So this is an ideal. So how do I think about this ideal? Again, if you're first year of grad school, you haven't seen anything before, I'm thinking maybe kind of an example of an ideal is a monomial ideal. When I'm saying that I pick a Yann diagram, any diagram like this, and I is the set of all monomials, so this is lambda not in lambda. Okay? So this is kind of all monomials. So if I'm saying that, yeah, kind of here I'm saying that my 1, x squared, y, x, y, this is y, it's y squared, y squared. They fill in the quadrant, and I take all monomials not in here. Then multiplication by x moves me to the right. Multiplication by y moves me up, but then this thing is closed and multiplication by x and y. All right? So now how this is related to all this business? So it's related because I can say, let's talk about the space C of xy mod I lambda. So this is basically the span of monomials in lambda. Okay? And so I can say, yes, so I can look at this example. So this was one of my examples for lambda. And I'm saying, what does multiplication by x actually do in the quotient by my ideal? So this element goes to this element. This element goes to 0. Maybe I don't even write this, right? So this goes to 0. This element also goes to 0 because this is contained in I lambda, and so this is 0 in the quotient, right? And then everything else is 0. So this is my matrix of multiplication by x. What? So I have a basis in c of xy mod I lambda, given by these three monomials in the diagram. I'm just describing the operator of multiplication by x in this basis. There is 1 2 by 2 Jordan block from here to here, and everything else is 0. What is multiplication by y in this basis? Well, it's that. And then the rest again is 0. So this is what I call maybe A. So this is multiplication by x. And then my B is multiplication by y. All right? So now I'm saying, okay, so let's do a version of this when I have two ideals. So I'm saying now I have t of xy inside ideal and inside ideal, where now I want xi to be contained in j and yi to be contained in j. All right, so how does it look visually in this example? We're saying, well, so I can take my, for example, j to be this and I to be that. How about this? I mean, again, this is boring example. Let's actually do slightly more interesting example. This one. Okay. So this would be my I, and this would be my j. So again, I is the ideal, everything outside of this diagram. J is everything outside of this diagram. In this example, obviously, j is contained in I because it's smaller than that. Now I'm saying, okay, so what does multiplication by x actually do? So if I start from, oh, this actually doesn't satisfy the condition, right? Yeah, that's a bad example. No, that should be fine. No. That should be fine. Sorry. Yeah, so if I have an element here, all right? So yeah, let's look at the ideals first and let's look at the quotient. So if I have an element here, so this is an element of I. So it is not in J, but if I multiply it by X, it will be in J now. And if I multiply it by Y, it will be in J now, all right? So what does it say about my matrices? So again, you have to translate everything to the quotients. So you're saying that you have actually the map from C of xy mod J, surjective map to C of xy mod I. All right? And the kernel is these two guys. That is the kernel. Right? Because precisely I'm saying, so yeah, whatever. That is the kernel. Maybe the kernel is J mod I mod J. Really? Okay. And then I'm saying, okay, so what is, if I just focus on this kernel? So this kernel, what is the multiplication by x? That's 0 on the kernel. And what's multiplication by y? That's also 0 on this kernel. And so that's what it is. So if you just look at J, yeah, so if you want to look at the matrix of multiplication by x and J, well, how do we kind of detect that this guy is in the kernel? Well, because this guy multiplied by y is 0 and this guy multiplied by x is 0. So this will give you some kind of 0 column or row in here, in multiplication by J. And then, I mean, this guy is not even in I, so there is no point of talking to him here. But it would, basically the constraint would be that for the bigger diagram, you would have a lot of zeros coming from this thing when you start multiplying by x or by y. So you have like this, in this case, I have two-dimensional kernel. This means that I have like, I think 2 columns of zeros in both x and y. And the columns are exactly the same place.
Eugene, I think you taught me this picture in first year of
Could
graduate school.
be. I mean, not this picture, but the hero scheme, yes. 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 Okay? Is it better with monomials and ideals? I don't know if it's better.
So everybody vanishes on the kernel. A, B,
Everything vanishes on the kernel. Everything. The kernel is really trivial. Yes. Yes. Yeah, but somehow, so again, it feels like a restrictive condition, and it is, but somehow the point is that, so at least like if you have just kernels one-dimensional, there is no restriction at all. It will be automatic. Like if I just have like one box at the corner, and you want to be an ideal, then this box must go to 0 kind of for x and y. Yeah, I don't know if it helps, but yeah, that's what it is. Yeah. Maybe I should say, so if you, this is restrictive on the diagram actually. Not every diagram you can remove two boxes which are like independent from each other. Or like K boxes. So from this diagram, I can't remove like 3 boxes because they will be dependent from each other. And if I have a diagram, I don't know. I mean, if I have just this diagram, for example, right? So like how many boxes which are independent from each other I can remove? Like this one, that's all. That's all what I can do. So in particular, there is no, so this correspondence is not surjective onto the Hilbert scheme on either side, because you can say, well, if this is my big diagram, there's no way I can find 2 or more boxes which are independent from each other. So it will project, but like it won't project to. So if I have a correspondence, I don't know, this kind of whatever, m, n minus 5, and whatever 1 for the Hilbert scheme. So you expect that you have projection just to Hilb n minus 5 and Hilb n, right? Which forgets the big diagram and the small diagram, but it does not. So this guy won't be in the image of this projection because you cannot find the other diagram so that the difference has 5 independent boxes. And the image of this projection is what is called Bernoulli locus, and there is a whole algebraic geometry story behind this, which I don't want to tell. But somehow it's that's kind of another important feature of this map. They are not surjective in either direction, actually. So you need to describe the image here, you need to describe the image here, and you need to kind of be careful about this. But the total space is smooth, and these guys are smooth. It's just like the maps are kind of a bit subtle. Okay, is it better? All right, okay. So let's go back to algebra. Where was algebra? Yeah, here is algebra. So I was saying that you can use these correspondences, especially Nakajima correspondences, which I still want, could I mention one thing, to define some interesting operators. And kind of the famous example, again, for Hilb n, this EM. I mean, there is only one vertex, so there is EM, generate let's call it positive, so positive half of elliptical algebra. And the relations are the following. So you write E of z, which is the sum of 0 to the minus m. And you have something like this. So you have E of z, E of w. What was that? Z minus qw, z minus tw, z minus 1 over tw is equal to E of w, E of z, maybe minus sign. And then that one you also flip. So you get w minus qz, w minus tz, w minus 1 over tz. So this is one relation, and then the second relation is something like E0, E1, E minus 1 is equal to 0. Okay? And so this is what is called positive half of elliptical algebra, and then lots of people, in particular Shipman and Vassaro, and Fagins-Maluk, they constructed the action. I mean, they checked basically these relations. So the way they constructed the action of elliptical algebra is they said, well, you have these operators, which I just defined for you using this correspondence and line bundles. And then the hard part is that they check the relations on the Hilbert scheme. And then in general, right there. Yes, Q and T is in the coherent K-theory. So the algebra is defined over Q and T, but like geometrically, so you have again two parameters from scalar x and y, and these are the Q and T, which might be slightly different from Q and T I had before, but it's some change of basis. Yeah, but somehow non-trivial content is that you have these operators and they satisfy those relations. So you have in particular relation number one, it's VOA equation, right? So you expand this in Z and W's. It's an infinite series of equations, and then you pick coefficients in different powers of Z and W. But this is really complicated relation. If you look at this, you have like 8 terms on the left, 8 terms on the right, and they're like matching each other, and there's no easier way to write this. The second relation, I mean, it's kind of mysterious for various reasons, but the first relation already is kind of not easy to control because you have this just lots of terms there, and there's just no way around this. And so in general, so people work this out, at least in this generality like we're working with. So in particular, there was a recent paper of Nicolle, Sal, and Schiffman. And then some related papers of different subsets of them. So they have explicit generators and relations in general. And I'm certainly not writing them, but again, for every vertex now, basically you have E of Z for every vertex. And then you have some quadratic and cubic relations for every edge, essentially. Which is tricky. Yeah. So quadratic relations, they're kind of that flavor on the top. But again, writing them for any quiver is messy. And then cubic relations are really crazy, unfortunately. So they wrote the cubic relations, but they're like really, really awful and much harder than that one. But they are what they are. So they figured out them completely. And there are no more relations. Again, I mean, there is a whole story which I don't have time to cover. If your quiver is like nice finite type, then you expect a quantum loop group out of here and so on, but let's not go there. We're focusing especially on the bad quiver, so let's look at that. All right, so now where we're going to, we want to define a different algebra, which is much bigger, but hopefully it slightly clarifies what's going on with the relations, or not, I don't know. Depends on your perspective, I guess. So our goal define a larger algebra. BKT of Q. And I'll start with an example and then I'll talk. And then, okay, start with an example. And then we'll explain what we expected, what we know, and so on. So for the Hilbert scheme, so BQT has, let me skip the Q, lots of idempotents. And I can draw them as vertices in a quiver. So it will be 0, 1, 2, ... And then we'll have generators which go between different idempotents. So there will be generators D plus, which go from K to K plus 1. There will be generator D minus, which go from K to K minus 1. Z1 through Zk, which go from K to K. And T1 through K minus 1, which go from K to K. Okay, so the picture, maybe I'll try to draw this and get bored. So there is nothing interesting at level 0, but there is D plus and D minus, and then there is again D plus and D minus. And then also here at level 1, you have a loop given by Z1. At level 2, you would have 2 loops given by Z1 and Z2. And then you have a separate loop given by T1. And so on.
Sorry, what are we doing?
Okay, yes, great. Slow down. Okay, so I'm defining an algebra, kind of. So I'm defining generators for some algebra.
And then algebra.
And algebra will act somewhere, and then we'll get there. Yeah, so this algebra will be more general than elliptical algebra, and like definitely different than elliptical algebra, but I'll explain the relation.
Okay.
So there will be some algebra.
It will be better for correspondences.
It will be better for correspondences, yes. Yeah, that's the whole point of this, yes. So,
I mean, for instance, one could hope that this algebra is easy to prove the relation.
yeah, easier at least to prove the relations,
You
yes.
can add this one to this one.
Exactly, exactly. Great explanation, yes. So the point is that this algebra is really about correspondences. And so if you want to do relations, like you still need to consider correspondences, but it's hard. But here, like we have correspondences already. So I want to define the algebra where I just have maps between correspondences. And so that's kind of the whole point. And I mean, let me finish this and then I'll explain this more carefully, what I mean by correspondence. But the algebra is just tricky to define by its nature. So in the Hilbert scheme case, I have, maybe
I'll say one thing.
I'll use colors. Yes?
The point is, when you compose two Nakajima correspondences, the result is definitely not a Nakajima correspondence. So that makes it hard to check any statistics. Because you have to figure out the hell you made, and then compare some other thing, which is more many. Whereas Eugene allegedly has built some correspondences which compose better.
Yeah. But they include my Nakajima correspondences as a piece. And so like whatever I can do, yeah, so they compose better. But I mean, kind of fundamentally, maybe, yeah, you look at that equation with this quadratic equation. Like this E of Z gives you some correspondence between n and n plus 1. The product of two E of Z's will be correspondence between n and plus 1 and plus 2. And then with some line bundle depending on kind of powers of Z and W. And so here you're saying, okay, you have this linear combination of something like 8 different line bundles on this correspondence is magically related to linear combination of 8 other line bundles on slightly different correspondence, and they give you the same operator in K-theory downstairs. That's kind of not obvious at all. And again, like in this particular case with the Hilbert scheme, that was done by Zhao in particular, but it's not easy at all. And so we want to kind of go around this and say, well, we want to define a bigger algebra with more generators, more relations. But first of all, the relations are easier than those relations because those are kind of hard. The relation, I mean, there are definitely more of them, but they're more elementary individually. And if we combine all the relations in a smart way, maybe we'll recover those relations. And then separately, the relation that I got here, they have more transparent geometric meaning, hopefully. And that's where we're going. Yes, and so I was explaining that at least on the level of generators, you have, so you have idempotent for different integers. And then you have, for each idempotent, you have these generators, d plus increases k, d minus decreases k, and z's and t's preserve k, whatever they are. Okay, and so again, I don't know if this picture makes any sense. In the K spot, I have two Q's. Yes, so I can say right away to simplify understanding. So this gives you just a affine Hicke algebra for K. So in particular, Z is commute, and then T's satisfy braid relations. And then, I mean, the usual affine Hicke relation between Z's and T's. And then kind of the only non-trivial, so I have for level K, I really have a affine Hicke algebra for of size K. And then the only interesting thing is how d plus and d minus interact with this affine Hicke algebra. And everyone starts, so I'm not writing the relations, but this is written. So basically, we have some rules how this d plus and d minus interact with this affine Hicke. And so if I want to get representation of the algebra in particular, for each k, I have to give you a representation of AHA. And then I need to find some d pluses and d minuses between them, where like they satisfy whatever relations I'm not writing here. Okay? K is, I mean, no, I mean, there's no n. You sum over all n. Yeah. I'll say the statement in a second, yes. Okay? But K is not related to it, no. Yeah, and so the point is that, so kind of the theorem, this is the theorem from last year, yes, 2 years ago, I forgot. So what we proved is that this, I can just look at the spherical subalgebra of this algebra. And then the claim is that this is precisely my elliptical algebra in this case. Okay, so what does this mean? Unpacking. So I can start from level 0. So in level 0, there are no operators whatsoever. It's boring. But I can start from here, go up several layers, then apply some stuff from this aha, and then go down back by d minus. And then altogether, this gives me an interesting operator from level 0 to level 0. And I can look at all possible ways of doing this. So I go up, then I do some aha stuff, then maybe I go up and down and like in all possible ways. And so eventually I come back and I get to here. And so how does it relate it to this representation? So I can say that my EM in particular, this will be something like d minus z1 to the m times d plus. So the EMs are the easiest possible things you can imagine. When you go up, then you do this loop several times and then you go back. But it's not super hard to check that EM satisfy the relations over there. It's an algebraic check. It's much more interesting thing to prove that there is nothing else. And so this EM really generates a spherical subalgebra, but that's what we do in that paper. So now what does this mean geometrically? So how to think about this BQT geometrically? So now I can take big space E. This is a direct sum over all D Q. So what do I get? Okay, so I have this space, whatever it is. So I can define it for D. So D minus 1 to D minus K. Okay? So again, this parameterizes some representations. I mean, let's say K, where the dimension of this guy will be D minus 1 up to D minus K. Right, so there is only one vertex, but we have interesting actions of x's and y's and whatever. So the dimensions, let's say they go down by 1 every time. And then again, we have this condition that the first by the last. So my A and B and J vanish on the kernel of pi. Okay? So now there is a N and a K. So what you were asking. So K is the length of this chain. All right? And then N is, I mean, basically D or D minus K, I don't remember, whatever. But like there are two different parameters here. So this thing is bi-graded nature. Okay? And so on this thing, I want to define the action of my BQT. So how do we define the action?
Wrong question. So do you have the E sub M? Is the algebra active?
Yeah. So this Z's are, the line bundles are invertible and the Z's are invertible, yes. So this is, I mean, in AHA, you usually allow them to be invertible anyway. Huh? Okay.
I can pretend that.
But yeah, let's say they're invertible. Okay. So anyway, so we have the action of BQT. And what is the action? Well, the action is actually easier because, okay, so we need to define this D plus and D minus. They're given by just two projections. So I can say maybe I'll have this M D minus K, and I can project down to, let's say, D minus 1 to D minus K. Well, I can project up to D minus K minus 1. I don't know. Okay. All right, so this has length K minus 1. Well, this has length k plus 1, actually. This has length k, and this has length k, all right? And so now we're saying, okay, so you have plus 1, yes, right. Great. Okay, so you have two projections. And then we're saying, so okay, so d plus is basically, I mean, up to some normalization, which I don't write. So this would be p plus pull back. D minus would be p minus push forward. And then, so I can go from, so there are actual maps within all the spaces. And I have nice pullback, I have nice push forward. These are like proper maps, whatever. And I can just define them. Again, there is some normalization factor, which I'm sweeping under the rug, but that's fine. And then my z's and t's, they are actually free. So z1 through zk, line bundles, which are this di mod di. Sorry, these are actually kernels again. These are not mods, but these are like kernels. This gi to g plus 1. And then ti are some again, so you have a fine Hecke action. And like, how do we actually know that you have a fine Hecke action without any computation? So you can say if they fix the first one, if they fix the last one, again, in the middle, you just need to find the complete flag variety of that size. And Dyck in the 80s, 70s, whenever tells us like whenever you see complete flag variation, you have a fine action. And this is really the classical story. So this is basically, again, I'm saying, so if I just forget, if I have just the first and the last, okay, then the fiber will be just complete flag variety of size k, right? Because the quotient is k-dimensional, and just the space of all possible complete flags. And again, this is because we can constrain that like the quotient is honestly trivial. There is no more checks that like I need the subspace in the quotient invariant under x or under y. Like that is precisely what is bad about these nested Hilbert schemes, because if you want to do something like this for the nested Hilbert scheme, you need subspaces which are invariant under x and y. But like if the quotient is 0, like x is 0, y is 0, I can pick any subspace I want. So I mark these corners and I pick any subspace I want. And this gives me complete flag variety as a fiber. And then on complete flag variety, Dyck told us ages ago that there is an action of Aha. We could just use that basically. Yeah, so there are like closed formulas, whatever, but it's not big deal once we figure out that, again, we can do anything we want. And yeah, and then this relation, where was this relation? That EM is d minus e1 to the m d plus. This is obvious here because I'm saying I start from Hilbert scheme, I go up. Like before we were saying, so my operator is like composition, going up, line bundle, and going down. Here I'm saying each piece is actually operator of my algebra. And I just take composition of these operators. And that's precisely what happened there. And so that relation is obvious. And then again, like checking the relations is not hard. In this case, you can use localization, for example, and just compute everything in fixed points. Everything is nice and smooth, and so everything just works fine. In general, you have to work hard, and that's kind of subtle. But in this case, everything is very clear. No. Yes.
Also, you didn't get rid of theorem.
Huh?
You haven't yet stated the theorem.
I stated the theorem over there. I think in this case, yeah, sorry, I will say the theorem, but yeah, so this is the theorem that this is an action of BQT. No, for this Q, like for the Hilbert scheme. Like I'm just doing this for the Hilbert scheme. For any Q, we'll get there. But yeah, there are two theorems here. One is algebraic, which says that like spherical subalgebra of this giant algebra is honestly elliptic Hall algebra. And then that this gives you actually an action of BQT. And that's also, yeah, so the theorem.
Yeah, but this, so you separated the second theorem plus previous implies the first theorem.
No. Great question. So we know that the action of elliptic Hall algebra on the Hilbert scheme is faithful. We don't know if the action of BQT on this whole thing is faithful, and it's unlikely that it is. So
You show that one of the operators in your algebra.
yeah, in representation they agree. Like, I mean, this statement is about representation, right? That I have a representation of both algebras when they actually agree.
You're saying it could have been this one thing, but what those previous people were, this 1, 0, BQT 1, 0 projects onto this.
Subalgebra. We know that subalgebra of the spherical surjects into elliptic hole. I think that's you get for free. But like in principle, we don't know if these guys generate the spherical, right? But like take subalgebra generated by these guys, that surjects into elliptic hole. That you get from the representation, basically. And then you need to check that they generate everything, and that kind of was the main bulk of the paper. And then you need to check that this is, because it's faithful, that kind of subalgebra is everything. That's, you can deduce from that, for example, yes. Yeah, but that's like non-obvious state. Like that took some time to prove. So that's pure algebraic. This is geometric, but this is saying, yeah, you just check that all the relations are satisfied, but that's actually not hard. Like, yeah. Essentially, I mean, we did this in a separate paper with Eric Carlson and Anton Mellet, but like, this is slightly different setup, so we have to redo it, but it's the same computation, whatever. Yeah. So yeah, this is done. Okay, and so then kind of what we know in general, so that is work in progress, so I'll just say this and then we'll see how much I want to say about this. So now, and so okay, so maybe I'll just give an idea and then say some other things. So before we had these generators, now we have a lot of generators. So now K is a vector. So you have KV for each V. Right? Because I have again a pair of representations, but I can measure the difference at every single vertex. And now I will have operators D plus, comma V, D minus, comma V. And then I have Z1. So the indices become really messy, unfortunately. So basically, that's kind of the basic setup, that for every vertex, you have one D plus and one D minus. And then you also have Z's and T's, which don't change the size. Now, this is the easy part. So these form the product over all V of ahas of size KV. So in particular, all these Z's and T's at different vertices commute. And that's kind of additional, very strong restriction that we want to put here. So this kind of commute at different vertices. And then again, there is some commutation between D plus D minus and some interaction between this and this. And we know how to write this, but maybe that's too much for this. But essentially, it's just the same diagram as you have here. You can do this diagram at any vertex separately now. Because now you can say, well, so maybe I have a chain. And again, from a chain, I can erase the first one. I can erase the last one. And I can measure where the difference actually happened. And so that's basically the idea for these operators. And the fact that you have aha with commuting at different vertices, that's easy to explain. Because I'm just saying that, again, the quotient is trivial. I have a bunch of trivial subspaces at every vertex. And then I put a complete flag in there completely independently. Because again, like the quotient is trivial, so here I put, if I fix the first and the last, I have a complete flag. If I do this at every vertex, now I have like the flag here and the flag here, but they don't talk to each other. There are no arrows between them precisely because the quotient is trivial. And so this means that I can put anything I want and they really would commute really nicely. So that kind of was one of our motivations for defining the spaces, but like turned around kind of in a more interesting way, but like we wanted this and somehow, and that was kind of natural motivation why we ended up with the spaces, because we want to say that kind of if I do something here and something here, they just don't talk to each other that much. And in the similar way, for example, you have a relation that d plus v and d plus w commute, and then d minus v and d minus w commute. But then if I have commutator of d plus v and d minus w, this is something which I'm not writing. So if I add something here and remove something there, then you need to control kind of how many edges you have between v and w and all that combinatorics. But if I just add some stuff here and here, because I just create more trivial stuff, it doesn't matter in which order I create this trivial stuff somehow. So that's the logic. And this type of a relation, this is also kind of interesting. So maybe I'll just say, so what Vivek was saying about these correspondences. So if you have something like M, okay, maybe I'll do this for just one vertex to explain, but this will be the general thing. So if I have something like this, okay, so I have two projections, to d minus 1, d minus 2. I have projection to d minus 1. But then I also have projection down to m d minus 1, right? And you have all of them. And so somehow, if I want to compute the commutator of d plus d minus, if I can either go this way and this way, or I go this way and this way, and I want to compare the result. So this is not a Cartesian diagram, but we have really good control of what happens in this diagram. So again, all the spaces are our spaces that we understand. And then there is some excess intersection formula, which basically does the job for you here. And so this relation we really understand really well. And the other relations are kind of similar, but like, yeah, we're writing this up and there are tons of indices and tons of relations. So this is really painful, but hopefully we'll get this. And again, the expectation, so yeah, so now just write everything as a conjecture because it's not completely written. So conjecture is that whatever this algebra acts on K-theory, on direct sum of all possible K-theories of these M's. So this we're pretty sure about. And then, I mean, at least there is a homomorphism from, I think, from this K-ha to the spherical subalgebra of this PQT. And we know some things about this homomorphism, but maybe it doesn't matter. So I just like send EM to whatever is written there for every vertex separately. And kind of, yeah. We definitely don't know that this is surjective, but we probably know that it's injective, and like we know some other properties, yes. Yes, I think so. Yeah, there is an easier way. I mean, there are easier representations when you can write this. So, like, yeah, so this would be the consequence of this if this is faithful representation, just a much easier representation when you can write this and check by hand, basically. But yeah. That's right, that's right. No, that is correct, yes. That implies that it's injective, yes. But then surjective, you actually need to work hard, and that's kind of, there is a whole interesting business there. And kind of maybe separate the interesting thing why we are really interested in this algebra BQT is because you can construct more operators. It's not easy to write some nice operators inside elliptic Hall algebra. I don't know if you've thought about this, but like, okay, so we have the generators EM, which were erased already, but you have some interesting operator. Typically, it's very hard to write it as a polynomial in EM. It's like almost impossible. So there are ways around it. Like Nicolle has this whole technique of shuffle algebras and stuff, but it's hard. And this way, I mean, we have more flexibility, so we can like cook up some really crazy composition when we start going up and down and like multiply by different z's and multiply by different t's and kind of we can do lots of things. And there are lots of operators which are like very natural from this perspective, and very hard to write if we just stay within elliptic Hall algebra with this like small set of generators. So again, the downside is, of course, we create more generators and more relations, but the upside is we have more flexibility and better chance to understand this thing kind of properly. So yeah, I think I'll stop here.
Question. So for K-half, you presentize it, it's just generated by these Nakajima correspondences.
Mm-hmm.
But if I just give you some random correspondence, two guys that have a big difference, does that define an element in K-half?
Sometimes. I mean, it's subtle.
So definition of K-half is really you need to. I never know. I just thought of K-half for any categories. Look at short like sequence, this extension.
Yes, but I mean, I think it's true that like under some maybe you need some extra assumptions, but like under some like pretty flexible assumptions is generated by this degree 1 guys, because you would say that again. So like in the Hilbert scheme, you can say, well, you can have something on commuting stack, but like once your Y matrix is nilpotent, you can filter it by some things and kind of inductively write it as extension of something. So anyway, so there is some argument why this is, maybe you need some loops to be nilpotent and you need to be careful, but model of that, I think people know how to prove that it's generated in degree 1 at this point, yes. Yeah. And there is also a relation with like this shuffle algebras for arbitrary quivers, and so this result of Schiffman, yeah, this Nicolle and Schiffman thing, they basically go through shuffle algebras to connect to Q-hub. And that's kind of a big thing, yeah. And that uses, I think, the fact that your K-theory is generated by tautological bundles, if I understand correctly. So for any quiver, you can take this equivariant K-theory, but it's actually generated by like Schroff-Anders of tautological bundles. And I think that's a true statement.
So if you strange relations with this K-ha or whatever, can you get that out of your conjecture function?
Yeah.
I guess abstractly, the way they should follow, but you can explicitly derive that.
Yeah, it's like 3 pages of formulas, but yes, I can derive it. I checked this. Yes, it's just really painful. Yes, we hope to write it kind of in a nicer way, but like right now, you can just we have those relations. We want to check this relation. Okay, we just manipulate with all the series and all the stuff, and like it's really, I can show you. It's like it's a painting. Like it's a wall of formulas basically. Like whatever. But like I was happy when like we checked that algebraically it matches up. Yeah. But that's really painful, and that's kind of one thing which we want to do better before finishing the paper.
So the title of smooth correspondences.
Yes.
So you have Nakajima correspondences as special cases. That is the way in which Nakajima correspondences are smooth.
They are smooth. We just have more smooth correspondences. Like the title is like emphasizing that our stuff is smooth and it's more general than Nakajima.
Compose two Nakajima correspondences. That will not be smooth.
Yeah.
That's what makes this whole case.
Yeah.
So is the cohomological limit of this
Probably, yes. I haven't tried checking this, but I think the answer is yes. Yes. Not that it will be like very easy algebra, but it will be like